In this section, we're looking at the compound and double angle formulas for trig. Now these are really important for us when we're simplifying trig expressions. Now with the compound angle formulas, I've put those here in a box and the double angle formulas underneath. I want to talk about proofs for these formulas. The reason for that is that when you get into, in particular your exams, it is expected that you're able to go through and work through proofs. So I'll do those mainly for the double angle. For the compound angle formulas, you actually need vectors to derive these expressions here from the relationships with the angles x and y in cos. But what I am going to do with these is look at the tan x take away y expression, and we'll actually use these expressions up here to help us with this one. Okay, so for our proof to see what tan x minus y is, I'm just going to write down tan of x minus y equals, and what we know for tan is we know that that's sine of whatever the angle is in here, which is x minus y, on cosine of that same angle. Okay, now we actually know, let's assume that we know what cos of x minus y is and we know what sine of x minus y is. So what I'm going to do is I'm going to actually put those in here. So I'm going to write down, right hand side, equals, and let's replace the sign. So we've got sine x minus y from our identities is sine x cos y, take cos x sine y, and that's over the top of cos x take y, which is cos x cos y, plus sine x sine y. Now things that you might notice here, with the cos, do you see that the signs are opposite? It's a minus in here, a plus here, a plus and a minus. With the sine, they're the same. The other thing you'll notice with the sine and the cos, when you've got the angles here, x and or the values x and y, with the cosine rules, you see that cos is together and sine is both together. They occur in pairs. Whereas with the sine, you've got the sine and the cos as a pair. So sine x cos y, and then cos x, so cos of the other angle, sine y. So these are actually fairly easy to remember as long as you think with the sine they're going to be the opposite pairs, sine and cos, and then the sine's the same. And with cos, the cos is together, so cos of x minus y is cos x cos y, so the two values, plus sine x sine y. So going on with this, what we can see now, it just looks ugly at the moment. Now a common trick when you're doing these types of problems is to look at where you're trying to go. You can see that you're trying to get some tan going on here, tan x, tan y. So we must have to get tan here somehow. The tip here too is this is a tan x. Now you can see here in our expression we have a sine x. So that would necessarily mean we're going to have to divide by cos x to get the tan x here. Now dividing by cos x on its own would be nice actually, because if we divide the top line by cos x, it will cancel that out. And if we divide the bottom line by cos x, it will cancel that out. So that's good. The other thing to look at here is that the second term is tan y. Now looking back here, we've got a sine y. So to get tan, remember that tan is sine over cos, we should divide by cos y. And again, that's going to be great because that will actually cancel this cos y out. So we're going to do that next. So what I'm going to do here, I'm actually just going to write down the lines that I have, and I'm going to divide them. I'll do this in a different colour. I'm going to divide the top and the bottom by cos x, okay, and then I'm also going to divide by cos y, and that's going to help me to get the tan x that I need here and the tan y that I need here. And let's write down the rest of what we had. We had the rest of this line. Now when you're dividing, you have to divide the top line and the bottom line by the same thing. So again, I'm going to divide the bottom line by cos x, cos y. Now this looks really ugly at the moment. Okay, it is going to look nicer. So when you're dealing with fractions as well, another nice hint is to split this up, because with fractions, for example, if you have 1 plus 3 over 3, this is the same as 1 over 3 plus 3 over 3. Okay, a third plus 1. And we know that this is 4/3. That's 1 plus a third. So you can split a fraction up into pieces. as long as you're splitting on the top, not on the bottom. So I'm going to do that here. I'm actually going to split this up. So I've got the first part over cos x cos y minus the second part cos x sine y over that cos x cos y. Big line. And I'm going to split the bottom up as well. Oops. Next there. And put that under there. Running out of room. So splitting everything up, and the reason why it's a great idea to do this, you can see the cancellations really easily. I'm going to do the cancellations in a different coloured pen. So you can see here the cos y's cancel, the cos x's cancel, the cos y's and the cos x's cancel. Now don't make the classic mistake, which is to think that if you have 2 over 2, they both cancel and you have 0. That's not right. Okay, remember that anything divided by itself is actually equal to 1. So this here is equal to 1, all of this. Okay, and again here you've got a nice no cancellation, but you can see, I'm going to just highlight in light blue, tan of x, tan of y, tan of x, tan of y. So if we put it all together now, what we have tan of x on the top there, minus tan of y, circled in blue, over all of this with the cancelling just turns into 1, plus sine of x, which I've circled, tan of x, excuse me, and the next part circled is tan of y. So what we've actually shown is that this is true. So tan of x minus y is tan x minus tan y on 1 plus tan x tan y. Okay, we've actually shown that. So we have shown, and ideally in a proof you'd have this as your first line, we've shown that our answer is equal to the right hand side here that we'd expect. So as required. All right. So the next thing that I wanted to do is to look at the double angle formulas. With the compound angle formulas, a great exercise as well, just to test your algebra and you're working with trig, try and derive this one as well. Okay. Again, these ones up here require the use of vectors, which we haven't covered yet. So for the double angle formulas, I'm actually going to go through and look at the proofs for all of these. Now you're welcome at this point, pause the video if you need to catch up or if you want to have a go at working with these double angle formulas yourself. I'm just going to erase everything here. And we can start again. Oops. Okay, the double angle formulas are similarly used for simplifying in trig, and they're actually derived really nicely from things that we already know. Okay, in particular, they're derived from the Pythagorean theorem, so the Pythagorean trig theorem that we've looked at before. So we're going to use that to help us. All right, and we're also going to use these compound angle formulas too. So let's have a look at, let's start with sine of 2x, that's a nice one. So let's actually do this as a formal proof now. So prove that sine of 2x equals 2 sine x cos x. So let's look at left hand side of this is sine 2x. All right, now for sine 2x, this is actually a double angle for x here. So what we could also write this as is x plus x, 2 x's together. Now as soon as I write it that way, you're going to be thinking over here. This is actually a compound angle formula. In this case, x is x here, but y is also x. So everywhere we've got a y here, we're going to put an x. So I'm going to say here using compound angle formula. And from now on, I'll just put CAF, okay, for my proofs, just to be a bit shorter. We're going to have sine x plus x is sine x cos x, oops, excuse me, plus cos x sine x. All I've done is I've used this expression here and I've put an x everywhere, an x where there's x's and an x where there's y's. Okay, so if we have a think about what we have now, can you see we've got sine x, cos x, cos x? It's exactly the same thing twice. It is 2 times sine x, cos x, which equals the right-hand side as required. So that's a formal proof. And to end it, we'll just put a little dot there, which tells us we've finished our proof. Nice. So we'll do another one. Let's look at cos 2x. Now at this point, you could have a go at this one without me. Okay, see how you go. It is going to assume that we know the compound angle formulas. So, oops. So again, we'll look at cos 2x. And the reason why it's great to know these proofs is, well, A, it can help you in remembering them if you need to remember them, and B, these kind of tricks are commonly used in proofs anyway, so it's really good practice. So again, we're going to write down left-hand side because that's what we have. This is what we have. This is what we want to prove. So we write down the, oops, helps if I write it down properly, the left-hand side that we have. So we're going to use, again, the idea that this is really cos of x plus x, and using the compound angle formula, we're going to have this one now. This is x plus x, but in our case, our y in this formula is an x. So using this formula, it's going to be cos x minus sine x sine x. And you'll see immediately these two things are the same. This is like x times x, which would be x squared. So this is cos squared x. And again, same thing here repeated. So that's sine squared x, which equals the right-hand side of that formula, which is what we wanted as required. Okay, so again, that proof, it's a nice one. Not doing this as a formal proof, but just quickly, so you can see where these other two forms come from. If we think about this answer here, and I'll write this in red, so we know already that cos of 2x is equal to cos squared x minus sine squared x. Now, hopefully you'll remember from our work with trig earlier on, as soon as you see the squaring, with trig, you think about the classic, which is that Pythagorean type expression. Now, this actually implies a couple of things if we rewrite it, making sine squared x the subject and making cos squared x the subject. Now, in both of these situations, we can actually use those to substitute into our red boxed formula here, which is for cos of 2x. So let's have a look at this. If we look at the first variation, I'm just going to erase this section. I'll do this in blue. So I'll call this, whoops. So substitute in the sine squared x in. What we're going to have is cos 2x equals cos squared x. So from here, minus, now we had sine squared x here, but we're going to replace that with this. So minus 1 minus cos squared x. And just expanding the bracket, it's a minus, that's a plus. You can see you've got, make sure that you put the 2 up, looks like a squared. You've got 2 cos squared x's, take away 1, and that is this variation here. So cos of 2x equals 2 cos squared x minus 1 is our first variation on cos of 2x. Cos of 2x is a really versatile identity. It's got a few different ways of working with it. And the next way, and you could try this yourself without me, is the other substitution, so the cos squared substitution. And this will work, this is this one here. We've used our Pythagorean identity to get this one, and it works exactly the same way. So we've got cos of 2x equals, in this case, cos squared x is replaced. And because we have this, cos squared x is this part, minus sine squared x, you can see there that we're now left with just a 1 minus 2. sine squared x. So that other variation here, cos of 2x equals 1 minus 2 sine squared x. Okay. The last one, you can stop the video if you want to do this one. Try the tan 2x one. I'll do this one just because it's a really nice one. It uses a similar trick to the compound angle formula. So I'll just get rid of this side here. Oops. All right. So again, think while I'm doing this, thinking about, okay, tan of 2x, what will I do with that? And remember that tan of 2x would have to be equal to sine of 2x on cos of 2x. Okay, now happily we know what sine of 2x is. We know that sine of 2x is 2. Let me just get rid of this bit. So sine of 2x is 2 sine x cos x, which we proved. And cos of 2x. Now the thing here is that we have a few options. Okay, now I'm trying to get to this form here, 2 tan x on 1 minus tan squared x. Because there's a 1 minus tan squared x here, there's a couple of ways that I could go. What I'm going to do is I'm just going to work with this one. It should work with any of them anyway, but I'll work with this one. So a cos squared x minus sine squared x. Try it with the others just to check. So let's have a look at this again. Going to use a similar type of reasoning that we did when we worked with our compound. So on the top I need to get tan x, yeah, 2 tan x. I've already got the 2. I've got the sine x. I've got a cos x in the way. Okay, so I think with this it's going to be really great if we could divide by cos x. That will get rid of that. But if we divide by cos x, then we just have sine x, so it's not enough. So what we're going to actually do is we're going to divide not by cos x, but by cos squared x, because what that's going to do is then give us the tan that we need. So I'm just going to write the lines that I already have. So 2 sine x cos x, that's the top line. And what I'm going to do with that line, I'll do it in purple, I'm going to divide by cos squared x. With black, I've got my denominator, cos squared x minus sine squared x, and I got that for what cos 2x is, that's over here. I just used that one. And again, I'm going to divide that line. So we're dividing the top and the bottom by the same thing. Okay. Now you can see with cancelling, let's do a bit of cancelling, that we've got cos x and a cos squared x. Well, one lot of that will cancel, so we'll just have a cos x left over. This here may be a little bit harder to see. Okay, so I'm going to rewrite that. So again, I'll just get rid of this part here to finish it off. Okay, so I'm going to write down what we have so far. We've got 2 sine x on cos x because of the cancelling. We've got denominator cos squared x, and what I'm going to do, just like over here where we split up the fractions, split it up. So the first thing over cos squared x minus the second thing over cos squared x. Now you can now see for our final bit of cancelling, this is equal to 1, and here this is going to be tan squared x. So our final answer is going to be equals, oh, and this as well, so tan x here, 2 tan x on the top. This is 1 cancelled, minus, and this is tan x, but it's tan squared x. So therefore, what we've shown is that tan 2x equals 2 tan x on 1, take away tan squared x. So those are the proofs for our double angle formulas and one of the proofs for the compound angle. Try proving the other compound angle formula as an exercise.